And I'll put a time here, starting at 3:02. All right, so let's go chapter 16, number 65, page 1. And to get us started, let's me use my phone again. Phone had been freezing out on us a few times. I was getting tempted to switch over to my to the whiteboard, but I think I like the phone a little bit better. I know that I don't write very cleanly on the computer screen. This stylus is kind of challenging here. All right, let's see. Okay, so let me find those questions again. All right, scroll down. Number 65. All right. So I think this one, well, maybe I shouldn't say because I'm not 100% sure, but I was thinking it was a little bit like the 57 and 58 we did earlier. A string on a musical instrument is held under tension T and is extended from the point x equals to 0 to x equals L. The string is overwound with a wire such a way that its mass per unit length, mu, increases. Yeah. Okay. So unlike the tension changing, the mass density changes. Okay. But it's still going to be a variation in some calculus. Find an expression for mu as a function of x over this range. All right. So for starters, then maybe I will help my ability to find this equation by making a graph. So if this is the x-axis and this is then the mass density, it says here essentially that the string is going from 0 to L. Okay, so here's 0 and then here's L. And let's see. And here's a big piece. It says it increases uniformly. And that's a code word, to say it has the same rate of increase. So it has the same slope. It's a straight line. Okay. So I know I'm going to have a line between these two. All right. So it increases uniformly from mu naught. So maybe I'll just put here a mu naught. So right here is the density mu naught at x equals to 0. And then it is increasing. So I know that the slope is upward. To mu sub L. And so maybe I'll just make a higher point right there, and I'll just make a straight line. Okay. And so the height right here is mu L. So we go from mu naught to mu L over this range of, or excuse me, I don't want to use range because that's usually implied vertical, over this distance of L, over the domain of L. Okay, and then let's find the function. So I guess I'll start by just kind of reminding you the equation of any line is y equals mx plus b. M is the slope and b is the intercept. So in this case, on the y-axis, I'm plotting mu. Okay, so there's going to be my function. I'll start with the slope. The slope is the rise over the run. All right, so the run is L, and the rise would be the difference between these two values they talked about, mu sub L and mu sub naught. So mu L minus mu naught over L. So there's the slope times x. And then B is the intercept, which is just mu naught. And that's probably good enough. We might do a distributive property, but because we could put the mu naughts together, but it's kind of nice, I think, left in this pattern. So that would be my answer for the equation. In fact, I'll take this as an opportunity to jump over to the solutions. Scroll down to 65. 65, or is 65A, and see what how they write it. And they write it exactly the same way. Oh, good. And they actually, looks like they got there the same way too. They didn't draw a little picture, but they thought of it as a line with a slope and an intercept, I think. Maybe they did 2 points. So maybe not real sure, but let's not study that. I think they did slope intercept. It kind of looked like could have been a 2 point, because you make the equation by a line, either by 2 points, and there's that method, and then there's the, I guess I call that the point slope method, and then there's the slope intercept method. All right, so I'll do that one first. Then B says, show that the time interval required for a transverse pulse to travel the length of the string is then given by this equation. All right, so here is where 65 kind of parallels what we did earlier with 57 and 58. So I'm gonna do that. I'm gonna say, okay, velocity is then the distance traveled over time. And if we're talking about a small distance and a small time, or a long distance and a long time, that'd be the average speed. But for this particular problem, since the density changes, the velocity changes. And so coming back here where the density is lower, the pulse would go faster, and then as it moved along, it would slow down as it got more and more dense. So it's kind of nice to rearrange this equation to say that if you had a small section of this wire, so let's say it was here, and since the density increases, I'll just kind of flare it out. But they made it sound like a string is overwound, not that it's one solid string, but I'll just kind of flare it a little bit, not much. Don't really know how much here, but I do know this, that if I made a little pulse here, it would travel along. And in parts of the string where the density is low, the velocity would go fast. And because it's fast, and that's a big number downstairs, it wouldn't take much time to go that short distance. And so a small time for a short distance. But later on, when that pulse is here, the density's high, the velocity is low, it's going to take a longer time to go that same amount of distance. Anyway, to get then the total time, we would want to add up all these little microscopic amounts of time, and that's where our calculus comes into play. And instead of writing our integral over time, we can replace that with an integral over space, and that's why we needed a connection between a small amount of time and equals to a small amount of space divided by that velocity. So that's the integral we're going to do. And that was the same logic, again, that we started on number 57 and 58, was to go back to physics 121 and how about distance, time, and velocity were related. Now, on this one then, we can then also say, and so I'll leave this equation alone for a moment. But velocity, which is the tension divided by the mass density, and the mass density is what we did earlier. It would be this mu L mu naught over L times X plus mu naught. And so that would be our equation that would be for the velocity. So I'm going to put that in here and say, okay, so let's do an integral. Here's my dx. And in place of velocity, then I will put and I'm going to break this into two pieces. It's the square root of the tension over, and since it's in the denominator, since the velocity is this, and so this would be in the denominator, and then this would flip and be on top. So this would be the square root of, should give myself a little better space, mu naught L, or mu L minus mu naught L times X plus mu naught. And this puts the integral on top instead of the bottom. So now that I think about it, maybe this will be mathematically easier. Conceptually, it's the same kind of physics, but might be mathematically easier than we did in 57 and 58 because we had that in the denominator. Although then we did a U sub and it raised it to a power and it was in the numerator. So, all right, maybe it's just kind of the same thing. All right, so what I have, and so let me pull out the square root of the tension. And then let me just write this as instead of writing a square root, let me write it to a power of 1/2. How about that? But writing this here as mu L mu naught over L times X plus mu naught and then the dx. So I'll just change the order and write the square roots as a power of 1/2 and then the square root of the tension in front of the integral.
Um, could you explain really fast why you flip the root t over in the step before the very last step?
Yeah,
Could
let
you
me
explain that
see if
again
I
really
can do
fast?
it here. Here's the dx. And so let me think of the velocity here as a square root of the tension over the square root of all this good stuff.
Okay, that makes more sense now.
Okay,
Thank
yeah,
you.
then all right. And then it's a compound fraction, so you flip it. Yeah. Okay. All right. And this, I think we had that discussion earlier. Looks like a good recipe for a U sub in our trig. So I'm going to do a U sub, but like last discussion, I want to stay away from the symbol U because U looks a lot like a mu. And I think it was Hunter's idea to, so let's call it alpha. So I'm going to follow that. So let's do it an alpha substitute. So let's call alpha equal mu L minus mu naught over L times X plus mu naught. And so that would mean D alpha would be mu L minus mu naught over L dx. Okay. So doing a little substitution and maybe making our integral simpler that way. This right here just then becomes alpha to the 1/2 power. That's why we like to do that. U sub or alpha sub, how we want to call it. Okay, so there's my alpha sub. And then, of course, the dx would be this thing. And so I got to solve dx by putting that to the other side. So that would be an L in the numerator and a mu L minus a mu naught in the denominator.
I think you froze.
And then a d alpha and froze again.
Yeah, you froze.
Camera froze.
It was an alpha freeze. Don't want to use you. All right, I'll disconnect my screen and see if we can share it again and figure out why this is doing it more than it used to.
Maybe the new Zoom update.
Yeah, well, this is definitely the first time I've used the Zoom update. And
I know ever since I've updated my Zoom hasn't been working how it used to, so maybe same thing's happening to you.
Maybe. Yeah, maybe. Okay. All right. So I should have looked a little closer where it froze before. But let me just come back here. So I'm going to do this alpha sub. And so everything up here is my alpha. So that just becomes alpha to the 1/2 power. And then, of course, the part that makes the U subs a little more challenging is then you got to do the differential substitution. So in place of dx, I move the L over there and then this difference underneath. So that's that. And then the d alpha. But of course, the neat thing is those are just constants. So I'm going to take those constants and pull them in front of the integral. And of course, now we've got an easy integral to do. That was the whole point, is now we just raised to a power. And so I'll actually do the integration. So let me leave the stuff in front alone. And you take alpha and you add 1 to the exponents. So it's already a half. So if I add 1, that's 3/2. And then you divide by the new exponent. And then there's some limits, which I'm just going to represent with 2 circles for the moment, because they're probably better listed in terms of x. So I'm going to switch alpha back to x before I put in the limits. Okay, so over here, I got L on the top. I got the square root of tension. I got mu L minus mu naught. And I'll even take this 2/3. And that's that compound fraction again. So I'm going to flip it. So that becomes a 2/3. Okay. And then this is the alpha to the 3/2 power. And alpha, I'll come back up here. It is a mu L minus mu naught over L times x plus mu naught. And now I'll put in my limits in terms of x. And so our limits of x were from 0 to L. Okay. Continuing on. And just because it's tradition, I'll move the 2 in front of the L and the 3 down here in the denominator in front of the square root of t. And then I'll have the mu L minus mu naught there. And so now I need to put in my limits. All right, so the first one would be mu L minus mu naught over L times L plus mu naught, and that would be raised to the 3/2 power, minus, and then the other limit would be putting in the 0 here. And so that term goes away, and so it would be just mu naught to the 3/2 power. Ooh, 3/2 power. Not sure I like that. All right. So I think we've done that right, and it's even tempting to stop here, but it says show that it would look like their equation. Now, their equation does not look like my equation. So let me keep going a little bit. Maybe one of the obvious steps is right here. Cancel the L. Oh, actually, that simplifies real nice. Okay. So I shouldn't have tried to stop there. There's a little more simplification that can go. Because once I cancel the L and then get rid of the inside parentheses, then I've got a mu naught plus a mu naught. So those go away. And so this is a mu L to the 3/2 minus a mu naught to the 3/2. Ooh. Now, looks like they did some interesting algebra. And I kind of see what they did on the bottom, and just, let's see how that works on the top. Okay. So, all right, I'll keep going. To be quite honest, I kind of like it in this form, but they went a little further. Okay.
Could You scoot that top page over to the left a little bit.
Yeah, yeah, sorry.
Thank you.
Okay, I'm not 100% sure. Let me tinker with some math here, but it looks like in the bottom, I can see it better. I don't really see it yet in the top. But let me remind you of one of your algebra identities. If you have the difference of two squares, so an a squared minus a b squared, that is a plus b times an a minus b. And the bottom to me doesn't really look like the difference of two squares until you write it this way. You could write it as mu L to the 1/2 power squared minus mu naught to the 1/2 power squared. And then we continue to have this mu L to the 3/2 power. And I think they're going to play some kind of similar game. And I got to see what that is. Oh, I see what the game is. Okay. Well, let me just write it like that for a moment. Okay, now I see it. All right. So I'm not sure I would have done this, but all right. All right. So this right here is the difference between two squares. So we could write this as mu L to the 1/2 power plus mu naught to the 1/2 power multiplied by mu L to the 1/2 power minus mu naught to the 1/2 power. Okay. Like I said, I'm not sure I would have thought of those as being the difference between two squares because you got a square root, but that's okay. Now, I think they did it because in this other piece, and let me not write it out, but let me remind you of the difference between two cubes. The difference between two cubes, and I'm going to have to think hard on this one, is a minus b, and then an a squared plus, and I remember it as an ab, but I think we're going to want to write the b squared first. And I'm pretty sure that's it, but I need to take a second to multiply this out to see if it is true. So let me do that. So a times each of these would be a cubed plus a squared b plus ab squared. And then the minus b multiplied out would be minus a squared b minus ab squared minus b cubed. And then these inner ones should cancel. So the plus a squared b and the minus a squared b, yeah, and the plus a b squared and a minus a b squared would cancel. And sure enough, I'm remembering correctly. Okay, good. Whew. Those are easy to forget, especially when you get my age. All right, but you guys are young and healthy. You got good memories. All right. So let's then come on down here and continue to play with this arithmetic. I'm probably going to need more than one line to write this. You see, I've already wrote this denominator as a mu L to the 1/2 plus a mu naught to the 1/2. And then times a mu L to the 1/2 minus a mu naught to the 1/2. Okay, so that's writing the bottom of a difference between two squares. But what I'm trying to point out, and now I can fill this in, is I could have written this top here as the difference of two cubes. And then use this algebraic identity to write it out. So the A and the B, so this would be mu L to the 1/2 minus mu naught to the 1/2. So that's the A minus B. Then I would have the A squared. So this would be mu L to the 1/2 squared. And then the AB would be the mu L to the 1/2 and mu naught to the 1/2. And then the B squared would be the mu naught to the 1/2 squared. Okay, now I begin to see why whoever wrote this solution kind of liked this. It wouldn't have been my first obvious choice, but it is kind of cool to see that this factor in the numerator and an identical factor in the denominator cancel off. And so you could argue that is simplifying things a little bit. Then we're introducing all these square roots. And so I kind of question if that's better, but let's see what we're left with. All right, so in the bottom, we're left with mu L to the 1/2, which I'm going to write as a square root, plus mu naught, which I'll write as a square root. Okay, so that's what's left in the bottom. And in the top, this, which looks like a square root till you square it, would just be mu L. And if we jump all the way to the last one, the same thing happens. That's a mu naught. And then these can be combined together as the square roots of the two, known as the geometric average. So interesting that this is a combination. This would be the arithmetic average and the geometric average. And so we have an average. Kind of makes sense. We're looking at the total time. The overall time would be somehow related to some kind of average effect. But kind of interesting that it's a combination of geometric and arithmetic averages. Anyways, I think that's it. Let's see, mu naught, it's right here, mu L, square roots. Okay, that's good. There's the 3, there's the L, there's a square root of T, there's a square root, yep, good. And it matches. So quite a bit of your algebra identities there that reduce it down to their form. And yeah, as you know, different equations have different forms, and they can have their different advantages depending on how somebody's using them and looking at them and studying them. So this, I can see how it could have its advantages. I don't like all the square roots, but I do like to see the geometric and the arithmetic average in there. I do really like that. So maybe that's a better form. Anyways, nonetheless, that's what we're asked to prove. Yay. Another tough one. So yeah, those last 3 tough ones, 57, 58, 65. Good. Glad we worked through them. Actually, I'm kind of a little surprised nobody asked earlier in the week, and I made a video of these. But maybe because of the last 3, it's takes a while to get there.
These, the last 3, 57, 58, and 65 would be too long for something that's on a test, right?
Yeah, the way they're written. I will tell you, I like that there's some variation and some calculus in there. That's really kind of make it an advanced problem, a good problem that would be between deciding if somebody deserves a B versus an A. But like this last one was loaded with algebraic identities that, in theory, you should still remember. But I find that when I give problems like that, I make the test becomes more of a math test than a physics test. So I I try to stay away from things like that. Things that, or if you need like a trig identity, you know, I try to provide the trig identity in the question. Well, actually, that's with closed book. You guys now with this online stuff, you know, it's open book, so you can look it up. By the way, as a side note, we're going to see a lot of trig identities. So that's coming up in chapter 18 next week. So keep appendix B and survey in the back of your mind going, oh, what was the sign of A plus B again? So usually students, I could be wrong here, but usually students remember this one, the difference between two squares. But the difference between two cubes is used a lot less and a little bit less likely to memorize. And I too, I was looking at that one going, what the heck did they do? And it took me a couple of lines before I figured out where they were going with it. I saw the difference of squares right away, but that one I didn't see right away. All right, so if you guys are good with that one, I'll move us on to, I think I saw another one in there, number 15. So chapter 16, number 15, page 1, and I'll even write here 123, number 15. Looks like the time is about 3:34. Nice. Okay. And so let me scroll back up to the more beginning ones and presumably easier ones. We'll see here. 15. 15 says, write an expression for y as a function of x and t for a sinusoidal wave traveling along the rope in the negative x directions with the following characteristics. Now let me pause right there, because a big point of this chapter was to get you to understand the general simple wave being a sine, and I'll just write the general form like this. And so there's an amplitude, and this is connected to the wavelength. This is connected to the frequency. The plus or the minus is connected to the direction. And then the phase, what we call the initial phase, is really related to what we call the beginning conditions. When does x and t equal 0? What is the value of it? And if we have a chance, we should probably call this time 0 and position 0. That way phi comes out to be 0. But of course, we could put the y-axis here, and then phi becomes a negative pi over 2. We could have it here, and then phi becomes a negative pi or a plus pi. So there's a lot of places we could put the y-axis. And so depending on what freedom we have of looking at this, and I think the best one, if we have as much freedom as possible, is to set it up so phi equals to 0. All right, so we are asked to write the equation, okay? So we'll need the amplitude, and the amplitude is just given straight up as 8 centimeters. We could leave it as 8 centimeters. There's nothing here saying we have to do the SI units, but I'm going to go ahead and just put it in meters. Usually that reduces any complicated problems. So there's the first thing they did. They give the wavelength. Now, the K is called the angular wave number, and it is, of course, physically related to the wavelength. So to get the K value, I take 2 pi and divide by its wavelength, and that's the next piece. They said the wavelength is 80 centimeters. which I don't know if it's necessary, but I'm going to put it in meters. So it's 0.8 meters, and grab a calculator and say, okay, 2 pi divided by 0.8. And then that would be a 7.85. And the units would be what we call a per unit. And so 7.85 per meter is the angular wave number. So that's another part we need. Now they also give us the frequency. And so we would need that for the angular frequency, 2 pi times the regular frequency. So 2 pi times 3, which makes 6 pi. The units here would be hertz, which we could write as per second. We could even put it as radians per second. We could even make it a decimal, 6 times 3.1415, but let me just leave it with a pi in there. Makes me think I should have left the pi in here, but then I would have a decimal and a pi, and that always bothers me. So if I'm going to go to a decimal, everything's a decimal, including pi. But if I have some integer number, I'll do an integer pi. That's just kind of my go-to picture. We'll see what the answer does. So there's the omega. Now they can give us the phi, because they say at y equaling 0 position and t equals 0 when time is 0. Okay, well, I guess that's what I said, that, okay, let me put this in. Let's put in y when x equals 0 and y equals 0. We would have a sine of the phi. And of course, we know the value of a, but they're also saying that at t, we get, let's see, and we want at x equals to 0, equals to 0 at time equals 0. They wrote it in a weird way, but okay, I'll put 0 here, which means sine phi equals 0, which means phi equals 0. And so those are what I was mentioning here, the easier ones. And so, okay, so there's phi equals 0. All right, so now I think I finally have everything. So I can write this wave equation. Y is a function of x and t is equal to its amplitude, so 0.08 sine. The k is the 7.85x. Now the direction of travel. What did they say here? Function of x and sinusoid traveling in the negative direction. So we put a plus for a wave traveling in the negative direction. Then the angular frequency is the 6 pi t, and the phi we just reasoned out would be a 0, and so there should be the mathematical equation for this wave. And jump over to the solution and scroll up to 15. We're just looking at 65, and let's see, they got the 0.08, yeah, so they did it in meters. Then they got the 7.85, good, so they did it in the decimal. They got the plus, good, and then they did the 6 pi. They left it as a pi since we hadn't gone to a decimal yet. Nice. Okay, so we got the same thing. I think there's a B to this one, so 15B says, what if? Write in an expression for y as a function of time.
Real quick, Dr. Young.
Yeah.
I just had a quick question. When I look at the solutions, they have it says 8 centimeters in front, but then it has the 7.85 inside the sine function. And that's sort of confused me why they would leave one in centimeters and have the other one in meters.
Okay, I guess I got 2 questions for you. You agreed mixed units is a little interesting, and I'll talk about mixed units. Sometimes that can be useful, okay? And I think it can be, but you said you were looking at the answer and it had centimeters in front, because I don't see that. I see meters in front. I see 0.08 in front.
Huh. Mine, looking at chapter 16, the answers that we have a link to online, and it says 8 centimeters.
Are
maybe
we
I'm-
looking at the same thing? Are you looking at the thing that I posted online with the solutions?
I think so. I mean,
Are you looking at
everything
the-
else.
Are you looking
There.
at the
If you
one?
look at the top, it gets converted to meters.
Okay, now, oh yeah, if you're just looking at the top where it says 8 centimeters, I'm going to the final answer where they put a box around it. Are you looking there?
Why I don't answer what I put? I'm looking at something different, man. What I'm looking at is just like a list where it just says y equals.
Oh, now wait a minute. There is a there is a part that says answers to even ones, but this isn't even.
I'm looking at odds. I'm looking. I mean, it says 15, but it's in that very first email that you sent us, right?
Yeah. That's why I'm really going bazonkers here. Going, I thought we were looking at the same thing, and
Let me see.
but like the first one, does it say problem? You know, it's got 16.1 and then 16.4 and then 16.10 and then 16.15.
No, what I'm looking at just says chapter 16, and then it's got a list of answers for odd problems. I don't know if I've been
And
looking
it's
at
got
the wrong
odd ones. Oh. And then there's this that says answers to odd ones. Okay, here. I'm going to send this into the chat. Let me send you a link that
Are you looking at homework solutions, Rylan?
Yeah, I mean, I've got a list of all the solutions in front of me, and it's from an email that the very first email we got from him, where I just clicked on this. It said, find solutions to homework here.
all right. Can you click on the link I just sent in the chat?
I clicked on that, and I clicked on odd
Okay.
answers.
No, okay, don't click on odd. Go back.
Okay.
Okay. Now, there's a table with 2 columns, and the column on the right says homework solutions.
Okay.
And this doesn't, so this gives you more than just the answers. This actually gives you the solution. And that's what I was looking at.
Oh, wow. Okay. I haven't even clicked on this yet. Yeah, this is a totally different ballgame.
Yeah, you'll like that column better because it's got the solutions and it's got both even and odd.
That's great. Okay, cool. Thank you for clearing that up. That makes things make more sense.
Yeah, now, and then, not to take too much time, but you guys just got me totally curious. So if I go down to 15 of chapter 16, what you were looking at, yeah, they did the mixed units. They did the 8 centimeters out in front. Now, I'll look at my paper. There's really not a necessity to have the units out in front match the units inside of the argument because of this reason. You have units for the K, and as long as they match the units for the X, these result in no units. And you're going to eliminate whatever you put them in. So if you put this in meters, you're just going to get a real number, and you're going to then calculate the sign of that in radians. Therefore, you still have the option to do your amplitude in any unit.
I see. Yeah, that
And
makes
so
sense.
you can mix them. In general, we don't like to mix them, but there's important reasons. In fact, I don't know, this pops into my head first, and maybe it's not a good example, but have you ever heard of how they measure water? They'll say there's so many acre feet. And what they mean by that is they're measuring the ground in acres and the height in feet. So an acre foot is a volume of water, where the area is measured in acres, but the vertical axis is measured in feet. And it almost seems like it would be better if it was in cubic feet or cubic acres. Why mix the two? But it's kind of nice.
Okay, cool.
Oh, the power company does the same thing. They sell you power in kilowatt hours. So they take the watt, which is a joule per second, but they multiply it by hours. And it seems like, wouldn't it be better to multiply it by seconds? The seconds would cancel off, and then people, when they're buying their power, it would say so many joules or kilojoules. It wouldn't, you could simplify the unit, but they mix them. And once you get used to it, you just kind of live with it.
Fair enough.
So mixed units are used periodically. Kind of better just to stay. Oh, another good one. Oh, yeah, here's a good one. When a car accelerates, sometimes you'll say the acceleration is 14 kilometers per hour each second. So you mix the hours and the seconds. But see, what you wanted is you want to be able to say that the car goes faster by 14 kilometers per hour every second. So after 1 second, it's going 14 kilometers per hour. After 2 seconds, it's going 28 kilometers per hour. And so your thinking is in miles per hour for speed, but your rate is in seconds, and you have mixed units. So mixed units can be useful. They can also be tricky. Okay, but
Cool.
yeah. So
Thank
anyways, side diversion there. That was kind of fun here. Okay, so now going back, let me get my back to the solution, not the answers to the odd ones, but the solutions. Okay, and then let me come back to the question. All right, so this was 15A. Oh, there was a B on here. So let me find B. B says, okay, what if? I'll write the expression for y as a function of x and t for the wave in part A, assuming that y equals to 0. Oh, at the point x equals to 10. Okay. So B is almost the same. Not quite, but the only thing different is the positioning of it. So let me come back to page 1. In other words, I would still have this general equation. It would ultimately go in the negative x direction, so I'd still have a plus here. It's going to have the same wavelength. It's going to have the same angular frequency. It's going to have the same amplitude. But what they're saying is I'm going to end up with a different phase. Because if I use a phase of 0, this would be one wavelength. And let's see, the wavelength was 0.8. So it would come back to 0 at 0.4 and 0.8. And then 2 wavelengths would be 1.6. 3 wavelengths would be what, 4.2. 5 wavelengths. Oh. Did I count right? 0.8. Oh, did I mess up here? Yeah. Okay.
3.2.
Sorry about that. Okay, so this would be 3.4. 5 wavelengths would be 4.2. That's what I did. I skipped one. Okay. Now, 10 wavelengths would then be 8.4.
I'm a little confused. Isn't each wavelength 0.8? So wouldn't 3 wavelengths be 2.4? Right? Because each wavelength is 0.8.
Thank you. I'm totally screwing up.
So you've been doing a lot of physics today.
2.4. Okay. So 1, 2, 3. 3.2. So let me try it again. So 1, 2, 3, 4. I was trying to do 5. So 5 would be what? 4.0.
Yeah.
Okay. So 10 wavelengths would be 8.0. And I'm trying to get to 10 meters. What I'm trying to show you is with this phase, at 10 meters, we would not be at 0. Oh, crap. And it's not 10 meters, it's 10 centimeters. So I'm really messing up here. So forget everything I said. I'm going down the wrong road.
Okay.
I'm trying, I guess 10 centimeters would be right here. And what I'm trying to show you is with a phase of 0, you would not get it at position 0 like they're asking. So you would have something that would look more like this. Oops. At 0 would be down here, and at 10 centimeters, it's 0, and then it goes like that.
Okay.
So there is going to be a phase, is what I'm trying to say. And so let's do this. At y equaling 0 position and 0 time. And now I need to just come back and read this right. Assuming that y as a function of x and t is 0, so time is 0, and at x equals 10 centimeters, the function equals 0. Okay, that's what they're trying to say. What if? Write an expression for the wave. For the wave in part A, but assuming that y equals to 0 when time is 0 and x is equal to 10 centimeters. Okay, so I'm going to use our previous equation and put in a value of y equals to 0, or maybe I should jump all the way to the top equation that started this conversation. Okay, so I have an amplitude, I have a sine of kx, and we still want it going in the negative direction, so I'll put a plus, and then there's the phase. And so the amplitude was the 0.0, what was it? 0.08. Okay, good. Then I have the sine. The k value, the angular wave number, is 7.85. The x is the 0.1. The time is the 0. And then we have a phase. And so if I simplify this by bringing over the 0.08, that's still a 0. And I have the sine of, and this would be 0.785 when I multiply the 2. And then plus a phase. Then when I do an inverse sine function, the inverse sine of 0 is 0. And then I would have 0.785 plus phi. And so this would tell me phi is a negative 0.785. And that's what I was trying to get at. I was trying to get at that, okay, the parameters they give you tell you where you have to put your axes, and that tells you what the phase is. So when I have a choice, I'd pick that as 0, but in part A, they didn't give me a choice. They told me it has to be 0, but it worked out to be a phase of 0. This came, again, they didn't give me a choice. They said it has to be 0 at time 0 and a position of 0.1. So that works out to be this phase. So the answer to part B would be that same amplitude, 0.08. Then it would be sine, and it would be the same angular wave number. It would still be a plus because it's going in the negative direction. It'd be that same omega. What was that omega? 6 pi. So it'd be 6 pi t. And then what's new here is a different phase. And so it would be minus 0.785 for the phase to meet the condition that they said. That is, have the string at position 0 when time is 0 and position is 0.8. All right, so hopefully that is also what they got. They got a little box. Yeah, good. Thanks.
Yeah, that makes sense. I think I found it weird the way they gave the initial conditions, the way they worded it. It was confusing to me.
Yeah. So you guys have heard me say this before, but it's, kind of making sure you kind of are reading the math and what each of those means really is helpful when you're reading the words, because the words is like, sometimes you can just read the words and you just don't know where to get started with the math. You're like, what are these words giving me? And so you gotta kind of recognize the consequence of where do these words fit in with the equation. And so you can see there in part B, I had to recognize that, okay, what they're telling me would just affect phi. So phi is going to be something different than 0, and I need to go back and find it, but the other things remain the same. So I didn't need to mess with those a second time. All right, good ones. All right, so let me come back here to the chat. Okay, so that was 15. All right, so Daniel, it's off to number 36. All right, so chapter 16, number 36, probably page 1. Let me write down number 36 at a time of 4 o'clock. Okay. And let's look at number 36. So scrolling through these, 33, must be the top of the next column. 36. Okay, so 36 says we have a 6-meter segment of a long string that contains 4 complete waves and has a mass of 180 grams. Okay, so I'm just going to make a dotted line and another dotted line and say, okay, what I've read so far, we're looking at a 6 meters worth of string. Let's do a dotted line across here for the string. They say it's vibrating, but they're also saying it represents 4 complete waves. Okay, so if I cut it in half and then half, so this should be 1 wavelength. This should be 2 waves. This should be 3 waves. And I didn't draw that very well. I was hoping to get a little more equally spaced, but ignore my terrible picture. But that's supposed to be 4 waves that fit in my 6 meters here. And of course, they did say the mass during that was 180 grams. I'll keep that in the back of my mind here. Okay. The string vibrates in a sinusoidal and has a frequency F of 50 hertz. All right, I'll write that down. And it has a peak to valley displacement. Now, here's where the picture can come into play here. So the peak is the highest point, and the valley or the trough is the lowest point. And they're saying that that's 15 centimeters. What I need to recognize is then that would be actually two amplitudes. See, because it would be going up and then down. So they're really telling me that twice the amplitude is 15 centimeters. If we want to go to meters or leave some mixed units, we'll see what they do. But I'll go to meters and then divide by 2. So this is saying the amplitude is 7.5 centimeters. Okay. So I've got the amplitude, I've got the frequency, I've got the mass of the string, the length of the string. Okay, keep going here. Then they say the peak to valley distance is the vertical distance from the furthest point of position. Okay, so, all right, nothing exciting there. A, write the function that describes the wave traveling in the positive x direction. All right, so again, like the last problem, let me draw the general mathematical description of a simple wave. And so like last chapter, a simple harmonic motion, but that was only a function of time. Now we have a function of space and time. Okay. And maybe some initial phase. All right, so I want to write this one. So it looks like I already got the amplitude. That's good. Let's go with the K value. Now, to get the K value, I need the wavelength. I guess I didn't write it up here, but 4 wavelengths would be the 6 meters. That's why they asked me to draw in 4. So that means 1 wavelength would be 1.5 meters. So the K value, the angular wave number, 2 pi over the wavelength, would be, by the way, maybe it's a passing note, because we did another problem where I said, be careful with the capital T, because in this chapter, we tend to use capital T for period. I mean, attention, and last chapter was period. Same thing here, we have a K for the angular wave number. Last chapter, we had that K for the spring constant. And so, not paying close attention, you can mix those. But there is no spring constant in this one, so I haven't come across that. We did come across other problems where we had a capital M and a lowercase m, and again, those can get confused too if you're not too careful. All right, so I'm going to put the 2 pi into my calculator.
A full wavelength is an up bump and down bump.
Yeah, it's not. It's not till it repeats itself.
Okay, cool. Thank you.
So just going from say 0 to 0 isn't really a repeat because this 0 is on its way up and this 0 is on its way down. We got to go to a 0 that it's on its way up. I think it's a little bit easier to see the wavelength when you go from crest to crest. You know, go from the top of this one to the top of that one, which is the same distance as from this 0, not this 0, but that 0. Okay, so the angular wave number is what I'm after. So it'll be 2 pi divided by 1.5. So that's a 4.19. And again, we got these weird units that we had to give it a name, but we call it a per meter. Because we do the per second, we give in honor of hertz. We need to give an honor here somewhere. Maybe it was so obvious nobody coined it and deserved credit for it. I don't know. Let's call it a Santa Barbara City College unit. Yeah. So it's 4.19 City College units. All right.
Why don't you coin it, Dr. Young?
Okay, so it's 4.19 Youngs. All right, but that's what it is. It's a per meter. Okay, so That's the K I need. Now, let's see. The other thing is, I think they told me the direction. I was chit-chatting so much. Positive direction. So I'm going to use the negative sign. Okay. Now I need the omega. The omega is the angular frequency. That's 2 pi f. And they said the frequency straight up was 50. So 50 times 2 is 100. So I'll just write it as 100 pi. And like I said on the other ones, I'll leave it as a pi just because when I have an integer times pi, that's my go-to. I just leave it as pi. But when I have a decimal times pi, it's like, oh, no. That's confusing. So make it just one big decimal. And then this is the hertz. Usually, though, we save the word hertz for the frequency. And then when we get to angular frequency, we throw in a clarifier radian and then write the per second. Sometimes you'll see hertz written with angular frequency, but that's not the norm. To help people kind of understand, are you talking about frequency in terms of what I'll call the physics, the oscillation? Or are you talking about the mathematics? And so are you talking about the angular frequency? Because our trig functions, need that 2 pi in them. It's too bad our trig functions don't repeat every one. Then we wouldn't have all these necessary for angular wave number and angular frequency. They would all be, our physics and our math would be the same. But it's not the way the world works. Okay, so yeah. And I guess you couldn't really have a world that way, because then your circle, your diameter and your circumference would be the same. You would have to have a one-dimensional world. So can't have that. All right. That's a fun geometry discussion here. What geometry would be better? Instead of having pi, maybe the ratio should be 4. So our dimension should have been a little different. All right, anyways, I carry on. Now, the last one here is this phase. Let's see, what information do they give me that would help me decipher what phase they want? Contains 4 string binary. Well, they say sinusoidally. So if you shift it, you don't have a pure sine, you have a cosine. So I think that is the information. It's not very strong information because we do get careless. We even call cosine waves sine waves just because it's just a matter of shift. But there is no other information. So I really think they want us to be drawing something that at time 0 and position 0, it has a sine shape when they say sinusoidal. So that's going to make a phase of 0. I'll check the answer, but I think that's what they're trying to say there. Okay, so that is enough information to complete writing down the equation. So the amplitude is 0.075 in units of meters. Then we have sine. The angular wave number is the 4.19, and that'd be x. Since we're traveling in the positive x direction, we put a negative sign, so there's the negative. The angular frequency would be 100 pi t, and I can just say the phi is 0 and not write anything. And I think this is the mathematical equation that they're looking for. And 36, scroll down. Now they write it in scientific notation, but we're saying the same thing. There's the 4.19. Oh, and then they multiplied it out to get 314. Okay, so same thing. But they didn't write it as a pi. And they got the negative sign and they got the phi as 0. So good. And then B, and this is the first time we've seen this one today, is the energy, or excuse me, I should say the flow of energy. So it's the power that is going down a string. And if I remember those video lecture right, I'm trying to do everything so fast that I don't think I derived it. I just said something like the book does a good derivation of it, and here is the equation. So because of that, I think it's a little bit harder to memorize this equation. We're also going to use it for sound waves here coming up. It's got to be modified because sound waves aren't quite the same as waves on a string. But we'll start there and then modify it in the next chapter about the energy flowing in sound waves. But this would be the energy flowing down a string wave. So if we don't really transmit energy by a vibrating string, but if you had like I do this sometimes. When I'm working in the yard, I'll have an extension cord and I'll plug it into the side of the house. And then maybe I'll have I have an electric chainsaw. And so I'll be way on the other side of the yard. And it gets caught halfway on a rock. And so I'll just make kind of a little hump in it. And I'll lift up my hand, and that little pulse travels on down, and it's carrying with it energy. And the idea is it's going to hopefully lift up that little rock and kind of kick it off, and boom, there it goes. Anyway, so the rate, the flow of the energy has 4 factors in it. They kind of make sense. I mean, obviously the velocity would come in. How quickly is it flowing would depend on the velocity. And since you're lifting the weight of the rope, you would think the mass density would come into play too, because, how much weight are you lifting? Sure. And then how many times you lift it up and down in a second would come into play. Sure, because that's its frequency. And then how high do you lift it? That would come into play. So it's not a surprise that all 4 of these are in here. It's a little bit of a surprise that they're squared, but nonetheless, that's the equation. All right, so let me answer this one by saying determine the power being supplied to this vibrating string. So now we just have to put in our numbers, and it's more of a plug and chug because we've got this information. We haven't done the mass density yet, but that was really right here. If I write it as 0.180 kilograms per 6 meters. And so just to make sure my units work out right, back here at the beginning, I had this 180 grams listed. I'm going to put it now as 0.18 kilograms per 6 meters. And the velocity, I guess we haven't done velocity, but the velocity is the wavelength times the frequency. So the wavelength is 1.5 meters, and the frequency is the 50 hertz. So 50 times 1/2, that's 75. So this speed's going to be 75 meters per second. Now we did do the angular frequency. That was this 100 pi. So now I'll square it. And I guess if I'm doing units, I should put my seconds there. So we got meters per second here. We got a second squared here. We got a kilogram and a meter there. Then the amplitude was the 0.075 meters. And we'll square that. And it looks like I'll need another page here to continue on. So page 2. But why don't I start with the units here. Let's see. This might take a couple of steps. It looks like here I got kilogram per meter. Right here I got meter per second. Right here I got seconds squared. And right here I got meters squared. And then that would cancel one of the meters. And if you remember, a Newton was a kilogram and just 1 meter over second squared. So this extra meter would make it a joule. So this part right here is a joule. And a joule per second is a watt. And that's perfect. We're looking for the flow of energy. Energy per second. Joules per second. Watt. All right. So the units work out great. Now let's try the numbers here. All right, so this is 1/2. This is 0.18 divided by 6. This is 1.5 times a 50 times a, and I'll just do this separate, a 100 squared and then times a pi squared. And then finally times a 0.075 squared. Enter. All right, so this would be 624 watts, or what are there? 746 watts in a horsepower. So 0.837 if I wanted to switch over to standard units, which I'm sure we don't, but horsepower. All right, so just under 1 horsepower, but I'm sure being a science class, we're going to have an answer in watts, but you engineering people might like the horsepower. Okay, so check the solutions here for B, and they got 625 watts. Good. Other than a small rounding difference and no horsepower, we agree.
Can you run me through those units one more time?
Sure. Okay, so the first one is kilogram over meter. The next one is meter. The next one is a hertz, which is a per second. The next one is radians per second. And so let me be real careful with radian. Many people think of radian as a unit, and that's not quite true. A radian is a qualifier. In fact, the definition of a radian is this. The ancient Greeks said, let's define the angle as the arc length divided by the radius. Well, the arc length is measured in meters and the radius is measured in meters. So sometimes you'll hear people say radians are real numbers. And what they mean by that is radians is not a unit. It's just a clarifier. It's a way to say, I'm not doing it in degrees. And so sometimes we throw the radians in there for clarification, and sometimes we take it out for clarification. We're always trying to clarify it, but radians is not a unit. It's a clarifier. It'd be like asking, how many students are Zooming right now? I guess I'm not even sure, so I flip over here. 1, 2, 3, 4, 5, 6. 6 of you, I think. So you would say 6 students, but students isn't the unit. It's a clarifier. The correct answer is 6. It's a number. There's no units that go with it. All right, so that's why when it came to the angular frequency, I didn't even put the radians. I just put the second squared down here because the radians, putting it in here now is going to make it worse, not better. But I do need to justify why I'm getting rid of it. And okay, and that's the short answer. Radians is just to clarify. How many students are Zooming? 6. That's good. It would be better if I said 6 students. So everybody knows, hey, there's 6 students, and then I've got Dr. Young on there twice. So there's 8 pictures, but there's 6 students, so just kind of a clarifier. And then, of course, this unit here is the square meter. Okay, so that's I'll call it the raw units. And maybe I should have done this grouping first, because that's a Newton. So then I'd still have my meters squared. I would still have a meter downstairs, and I'd have a second. And then maybe I could cancel off a meter. And then I should do this grouping. A Newton times a meter is a joule. So then I'd have joule per second. And that grouping is called a watt after James C. Watt and the invention of the steam engine.
Gotcha. So really a watt is a kilogram times a meter over a second cubed?
Oh, I don't think it was cubed. Let's see, it would be a kilogram meter per second for the Newton, then another meter for the joule, and another, oh, cube, yeah, another second for the rate. Yeah.
Trippy. Cool.
Yeah. And if you're curious, I don't know about the OpenStax book, but they break all these apart in the I think it's the back, no, front cover of the survey book, and they show all the breakdowns of the units down into SI units. So that could be helpful.
Thank you.
Yeah, cube. Yeah, and you can see why then we start giving them names, because if you always left them in kilogram meters and seconds, it just gets all these powers and it's not very useful. Yeah. Joules per second is very useful. All right, nice. Okay. And so, nice. So there's 36. All right, let me jump back over to the chat room. Oh, there's my link. It's a me. Okay. Mackenzie, you still here? I saw you earlier. No, okay. I don't know what she was meaning there. Oh, it's a me. A what? Yes. Oh, you are still here? How come I don't? Oh, you know what? There are more students zooming. Oh, there's a lot more students zooming. I didn't see the arrow. All right. Well, I was totally wrong about 6 students zooming, but good. That's good. That's really good. I like it. Okay. You already got your own units named after you. I'm still petitioning to have the per meter petitioned after a Young or called a Young. So we'll see if that goes through with the international committee. Okay.
I'll sign that petition.
Me too.
Yeah. All right. Well, how are we all doing? Thanks.
Good.
Appreciate you fighting for me. Yeah, I'm glad it made me scroll through. There's a lot more people here. Okay. So, any more we should do today? How are we doing on time? What for? Oh, 4:25. And we're on. Got 5 more minutes.
I think I've done about as much as I can do for now.
Yeah, I know by the time of the end of Friday, we're like, okay, this is good quitting time. So
Yeah, I'm pretty fried. I'm kind of done today.
But
Yeah, same.
thank you for going through all those like long 56, 57, 58. Those were real.
Yeah. Well, good. Yeah, I'm actually real glad we went through them. They were some long ones, but getting them recorded on video is nice. So when I compile all this together tonight and send it out, it'll be out there for people who are planning on working on this on Saturday or Sunday. They'll get there and go, oh, wait a minute, I should have planned more time. But
yeah, well, I've got it written down, but it'll be out there for me to go look at again too.
Yeah, a good point. Yeah, it's hard to digest that the first time.
Yeah, or if you miss something and like you can't figure out how to do it, I always check the list, see if it's one of the problems on the list, and if it is, I just go see how you fix that one little piece or something.
Totally.
You know, that's how I started the video lectures. I didn't make those video lectures with the idea that there was going to be a pandemic. I just made the video lectures because, so many students were like, I just need to see the second time, or I just tuned out for 5 minutes. And it would be so great if I could just do a replay. And I go, you know what? And it had been on my mind for years and years. And then I had a student who wanted to run the camera. And I said, perfect. And we did a couple times. And the first time it wasn't so good, but we got better. Actually, the big thing was learning to do a lapel mic, because you can do the video then from far away. And then when I turned to the board, you can still hear me. And that was a big thing. Anyways, and then to be honest, I did that video and I thought, well, maybe a few students will look at it. But after that, and I would show the students on the first day, they would go, oh, I'm so glad you have those, because I tuned out for 10 minutes and I went back and I looked at them. Other people said, my car broke down, I couldn't get there. And then I actually found it really convenient. Students would send me a question and they would say something like exactly what I just did. And I would just send them the timestamp to that video. And I go, here, look at this. This will help. And then students were, well, some of you actually were some of you in my, I guess you wouldn't have been in 123 last spring. But yeah, for the students who were there last spring, we kind of had a class discussion that I said, okay, it looks like they're going to quarantine us real soon. How do we want to run this class? And, about 5 people all at once just said, well, we got your video lectures, so we'll just keep doing that. And I said, yeah, that's the way to go. I'll just send out the video lectures and that'll replace the lecture.
That's what Doug did, because you have 121 film too. So when the
right.
pandemic first hit, he sent us your video lectures to finish the semester.
Oh, good. Yeah, I wasn't teaching when 21 last, but they were all there and all done and ready to go for anybody who wants to use them. Yeah.
I appreciate the video you put out this morning, the 121 airplane video.
Good. Yeah. And good. Yeah. And you too, Ed, if you're working on those homeworks in 121, know what Daniel just said, that I have a bunch of examples done in my video lectures of 121. Now, they're not explicitly for your homework, but if you want me to do one explicitly from your homework, just shoot me an email and say, hey, can you do this one? And I will.
Thank you.
Yeah, it's really very helpful, I think, and I hope you guys are getting a lot out of it. You must be. You wouldn't be coming here for 5 hours if you weren't getting something out of it. And say, look, it's just nice to see somebody think through the process and go, oh, that's what I missed. How did you know to take a derivative, or how did you know to take an integral? So.
Yeah, it's kind of like what you were saying earlier. Like, I mean, it's not that the math is always a problem for me. It's sometimes the wording of the problem and understanding what I'm trying to get.
Yep. Yeah, no, I totally get it. And I know it's not easy. So all I can say is keep hanging in there. And the way to get it is to practice on your own, practice watching other people do it. That's what the Zooms are all about and the video solutions are about. And practicing the homework, that's, it's the way the system works. So that's why we call you a student.
Great.
Awesome. Thanks, Mike. I'm going to be heading out.
Okay.
Thank you.
Yeah.
You guys bet. Let's see. I'll check the chat room. Yeah. I'll remember the filming equipment there when I took. Oh, yeah, that's right, Jack. You were, you were there when we did the filming. All right. Everybody's checking out. Well, you're all welcome, and I will be in contact. I'll
have a good weekend.
All right. You guys too. Stay safe too. Getting bad out there.
Hey, Dr. Young, real quick before you go.
Yeah.
So is the tests, are they going to be like the same as last semester? 9 o'clock in the morning and Just on.
Yeah, the one exception, I think I'll go a half hour earlier because that was a bit problematic for some of the engineering students.
Yeah, that's true. I was gonna ask if
Yeah,
we could get our schedule changed up again.
yeah. So you engineering people, yeah, I debated with that. Because there's only a handful of you, so I go, maybe I should just change them again like I did, but no, it's not that much earlier. So if I just go at 8:30 and do you 2.5 hours, you'll be done at 11. And your class is
Yeah.
what, 11:10?
Yeah.
Yeah.
Okay.
So
All
plan
right.
on
And
that.
those half tests are 3 questions, right?
Oh, well, 2.5, you might say.
Oh yeah,